Welcome to this very calm, very slow, very boring lesson on the periodic table. Today we begin with the first journey into the quiet, often forgotten history of one of the most important charts ever created by humanity, the periodic table of the elements. Let's begin. Chapter 1: The Age of Elemental Imagination. Long ago, before science was called science, there were philosophers and dreamers who looked at the world and tried to understand what everything was made of. They had no microscopes, no laboratories, only their minds and their senses. They thought that everything in the universe could be explained by four basic elements: earth, water, air, fire. These were not elements as we know them today. They were ancient ideas about qualities of nature. Earth was solid, water was flowing, air was invisible, fire was hot and transformative. These four elements were believed to combine in various ways to create everything in the world. This idea was very old. Even the ancient Greeks believed in it. Aristotle, the famous philosopher, spoke of these elements and their balance in the human body and in the cosmos. For over 2,000 years, this idea of four elements ruled the minds of scholars and healers. They did not test their ideas with experiments. They believed more in thinking than in testing. And so, progress was slow. The truth remained hidden. Chapter 2: The Rise of Chemistry. Then slowly change came. During the 1600s and 1700s, some thinkers began to question the old ideas. One of the most important was Robert Boyle. In the year 1661, he wrote a book called The Skeptical Chymist. In this book, he said something very important. He said an element is a substance that cannot be broken down into simpler parts by chemical means. This idea was new and powerful. It told chemists to stop thinking in vague symbols and start working with real materials, with experiments, with tests, with evidence. And so a new era was born, the age of chemistry. Chapter 3: Lavoisier and the Birth of Modern Chemistry. Now let us meet a man who changed everything. His name was Antoine Lavoisier. He was a French chemist, born in 1743. He lived during a time of revolution. But before he lost his head to the guillotine, he helped create modern chemistry. He carefully weighed substances during chemical reactions. He showed that matter is neither created nor destroyed. This became the law of conservation of mass. Lavoisier also created a list of elements. In 1789, he named many of the substances we still know today: oxygen, hydrogen, nitrogen. He helped remove ancient ideas like phlogiston, a fake substance once believed to cause fire. He created a foundation for chemists to classify the real elements. Chapter 4: The Element Hunters. After Lavoisier, the race began, the race to discover new elements. Chemists all over Europe started isolating strange new metals, gases, and powders. In the early 1800s, they found sodium, potassium, calcium, magnesium, and many more. These were exciting times. Each new element was like a treasure. But a problem began to emerge. There were too many elements, and no good way to organize them. Some had similar properties. Some reacted with acid. Some formed shiny metals. Some were poisonous gases. But how to put them in order? Chemists began to notice patterns, but they had no map, no guide, no periodic table, not yet. Chapter 5. The First Patterns. One of the first to notice patterns was a German chemist named Johann Wolfgang Dobereiner. In the year 1817, he found that certain elements seemed to form groups of three, called triads. One example was lithium, sodium, and potassium. They all reacted violently with water. They were all soft metals, and the atomic weight of sodium was about the average of lithium and potassium. This was interesting, but only a few triads were found, and the idea didn't lead to a full system. Next came a man named John Newlands. In 1864, he noticed that when you arranged elements by their atomic weights, every eighth element had similar properties. Like notes in a musical scale, he called it the law of octaves, but many scientists laughed at him. They thought he was being silly, and again his idea faded into history, but not forever. Chapter 6. The Russian Visionary. Now we come to the man who would bring it all together. A Russian chemist with long hair and a big beard. His name was Dmitry Ivanovich Mendeleev. He was born in 1834 in Siberia. He was brilliant, curious, and unafraid to think big. In the year 1869, Mendeleev sat at his desk with cards, each with the name and atomic weight of an element. He arranged them again and again, trying to find the perfect order. And then, as the story goes, he fell asleep. And when he awoke, he had seen the solution in a dream. He had arranged the elements in a table, where elements with similar properties were in the same columns, and the atomic weight increased across the rows. He left gaps where elements had not yet been discovered. He predicted their weights and properties, and he was right. When gallium was discovered in 1875, it matched Mendeleev's predictions almost exactly. So did scandium. So did germanium. His table was not just a list, it was a map, a framework, a prediction machine, Chapter 7, A Table of Elements. Mendeleev's table became famous, but not right away. At first it was controversial. Not everyone believed it, but the discoveries proved him correct, and chemists began to use it to understand reactions, to search for new elements, to teach chemistry. His periodic table changed science forever. Chapter 8. The table evolves. Though Mendeleev had built the first powerful table, it was not perfect. He used atomic weight to order the elements, but sometimes the order didn't fit. For example, iodine had a lower atomic weight than tellurium, but had to come after it in the table. This was confusing, until a young physicist named Henry Moseley used X-rays to count the protons in the nucleus of each atom, and he found a new truth. The elements should be ordered by atomic number, not atomic weight. This fixed the problems and completed the modern periodic law. End of section 1. You have now reached the end of the first section of your very boring but deeply informative lesson on the periodic table. In the next section, we will explore how the periodic table changed in the 20th century. We will cover the discovery of new elements, the noble gases, the strange and confusing F block, and the possible future of the table. For now, take a deep breath and let this knowledge settle. Good job for staying awake, or not. Either way, this has been a very boring lesson. You are listening to the second part of the hidden story of the periodic table. This section will cover how the table changed in the 20th century. We will discuss discoveries that fixed errors, filled in missing pieces, and helped scientists better understand the logic behind the periodic table. Let us begin. Chapter 9. Moseley and the Atomic Number. After Mendeleev, the table was widely accepted, but it still had small problems. Some elements were in the wrong order based on atomic weight. One example was iodine and tellurium. Mendeleev placed iodine after tellurium, even though iodine had a lower atomic weight. He did this to keep similar properties together, but the logic behind this decision was not understood. That changed in 1913. A young English physicist named Henry Moseley began working with X-ray spectroscopy. He discovered something very important. He measured the frequency of X-rays emitted by various elements, and he found that the frequency increased in a regular pattern. He realized that this pattern was related not to atomic weight, but to the number of protons in the nucleus of each atom. This number became known as the atomic number. It was the true organizing principle of the periodic table. Now, elements could be arranged by atomic number, and all inconsistencies disappeared. Moseley's discovery corrected the periodic law. It changed the periodic table forever. Sadly, Moseley died in World War I at the age of 27, but his contribution lives on in every modern chemistry textbook. Chapter 10. Noble Gases and the Eighth Group. For many years, a group of elements was missing from the table. They were invisible, unreactive, and hard to isolate. These were the noble gases. In the 1890s, British chemist William Ramsay began to discover these elusive elements. First, he isolated argon from air. Then he discovered neon, krypton, and xenon. Later, radon was discovered. These gases were different. They did not combine easily with other elements. They were inert. They formed a new group at the far right of the table. Group 18. The noble gases completed the table's structure. They helped explain patterns in chemical reactivity. They also helped scientists understand the concept of full electron shells, and they gave rise to the idea of chemical stability. These gases were not exciting, but they were essential. They were boring. Perfect for this lesson. Chapter 11. The electron enters the scene. In the early 20th century, scientists began to understand atoms in more detail. They discovered that electrons moved around the nucleus in energy levels or shells. The structure of these shells helped explain why elements behaved the way they did. Each row in the periodic table corresponded to a new electron shell. Each column contained elements with similar outer shell structures. This explained why elements in the same group had similar chemical properties. It also explained trends across periods, atomic radius, ionization energy, electronegativity. All could now be understood based on atomic structure. This was a major breakthrough. Chemists no longer had to rely on guesswork. They had a physical model to support the periodic table's layout. It made everything clearer and more predictable, which made it more useful. But still, more complexity was to come. Chapter 12. The lanthanides and actinides. As more elements were discovered, a strange group began to emerge. In the sixth period, beginning after barium, a long sequence of similar elements appeared. These were the lanthanides. They were soft, silvery metals, difficult to separate from each other. They filled the 4F orbital, and they were placed in a separate row beneath the table. This was not for chemical reasons, it was for space. If you put them in the main body of the table, it would be too wide to print. The same thing happened in the seventh period. After radium, the actinides appeared. These included elements like thorium, uranium, and plutonium. Some of these were radioactive. They filled the 5F orbital, and they were placed in another separate row under the table. These two rows became known as the F block. Even though they were part of periods 6 and 7, they were placed apart to keep the table compact. Many students find this confusing, which is why most people do not memorize the F block, but the lanthanides and actinides are important. They are used in lasers, in nuclear power, in magnets, and in electronics. They may be placed below the table, but they matter. Chapter 13. Filling in the gaps. In the early 20th century, many elements still remained undiscovered, but the periodic table helped guide the search. Scientists predicted their properties and where to find them. As technology improved, new techniques like particle accelerators were used to discover synthetic elements. One by one, the gaps were filled. Technetium was discovered in 1937. It was the first artificially produced element. Promethium was isolated in 1945. Then came transuranic elements. These are elements with atomic numbers greater than 92. They do not exist in nature. They must be created in labs. These include neptunium, plutonium, americium, curium, and more. Each new discovery confirmed the periodic law and expanded the table. Chapter 14. Naming the new elements. As more elements were discovered, scientists had to name them. At first, names were given to honor places, people, or myths. Curium was named for Marie and Pierre Curie. Einsteinium was named for Albert Einstein. Californium was named for the state of California. Some names were based on Latin or Greek roots. Others were based on atomic structure. But as more elements were created, naming became political. Sometimes countries competed to name the same element. For example, element 104 was claimed by both American and Russian scientists. Eventually, the International Union of Pure and Applied Chemistry, or IUPAC, stepped in. They created naming rules. Today, element names must be based on one of 5 sources: a mythological concept, a mineral, a place, a scientist, or a property of the element, and the name must end in ium, ein, or on. Naming elements may sound simple, but it can be complex and sometimes controversial. Chapter 15. The table becomes a teaching tool. By the mid-20th century, the periodic table was fully embraced. It was printed in classrooms, hung on walls, memorized by students, used by teachers. It became a symbol of science. Its clean layout, its numbered boxes, its bright colors, all made it iconic, but it also became overwhelming. There are many numbers, many rows, many symbols. So textbooks added charts, diagrams, and trends, arrows for electronegativity, lines for atomic size, shaded blocks to show metals, metalloids, and nonmetals. The periodic table was no longer just a list. It was a visual tool for learning and a guide for thinking about matter. It is now one of the most recognized images in science. Chapter 16. Where we are now. As of today, the periodic table contains 118 confirmed elements. The last confirmed was oganesson, element 118. It was named in honor of Russian physicist Yuri Oganessian. It was confirmed in 2006. The table now reaches into the seventh period, and possibly beyond. Scientists continue to search for new elements, element 119, element 120, and more. But as the atomic number increases, so does instability. Some elements decay in milliseconds, some cannot be confirmed easily, yet the search continues, because each new element tests the limits of our understanding and helps refine the periodic law. This concludes the second section of your lesson on the periodic table. You have now heard 4,000 words. 2/3 of the way there, we have explored how the periodic table evolved in the 20th century. We have covered atomic numbers, noble gases, electron shells, the F block, new discoveries, and naming rules. In the final section, we will look at the future. We will discuss superheavy elements, the island of stability, new periodic table shapes, and the role of artificial intelligence in chemistry. But for now, rest your mind. Allow this boring knowledge to quietly settle into your brain. Thank you for not falling asleep, or for falling asleep. That is okay too. This has been your second boring lesson on the periodic table. You have arrived at the final chapter of your very long and very slow journey through the periodic table. This is the third and final section. You have heard 4,000 words already. Now, we will complete the final 2,000. You are about to learn what lies beyond the edge of the table, the elements we cannot yet see, the structures we imagine, the mysteries we continue to test. Let us proceed. Chapter 17. Superheavy elements. The periodic table currently ends at element 118. Its name is oganesson. It is extremely unstable. It exists for only milliseconds. But this is not the end. There are more elements yet to be discovered. Scientists call them superheavy elements. These are elements with atomic numbers higher than 118. They are not found in nature. They are created in laboratories. Scientists smash atoms together at very high speeds. Sometimes, for a fraction of a second, a new element appears, then it decays very quickly into smaller atoms. These new elements are so unstable that their properties are hard to study, but they are important because they help test the limits of what atoms can be and what matter can become. Chapter 18. The Island of Stability. Most superheavy elements decay in microseconds, but some scientists believe that a group of them may last longer. This group is called the Island of Stability. It is a theoretical region of the periodic table, somewhere around element 120 to 126. In this area, nuclei may have special numbers of protons and neutrons. These special numbers are called magic numbers. They create a balance inside the nucleus, a stability. If this theory is correct, elements in this region could exist for seconds, maybe even minutes. long enough to study them, to see how they react, how they bond, how they behave. This island is still undiscovered, but many scientists are searching for it. The hope is that it will give us new knowledge about the strong nuclear force, about the edges of chemistry, about the structure of matter itself. Chapter 19. Will the table keep growing? As we create larger elements, a question arises. Will the periodic table keep growing, or will it reach a final limit? Some scientists believe there is a maximum atomic number, somewhere around 170. Beyond that point, the nuclei may not hold together. The electrostatic repulsion between protons becomes too strong. The atoms fly apart, so the table might have an end. But we have not reached it yet. For now, it continues to expand, one discovery at a time. Chapter 20. A new shape for a new table? As the table grows, its shape may change. The classic rectangle we use today may not be the best way to visualize the elements. Some chemists have proposed spiral tables. Others have suggested three-dimensional models, helical models that wrap around cylinders, circular periodic tables with radial symmetry, layered spheres that reflect electron shells more clearly. These new models are meant to show relationships more intuitively, especially among transition metals, lanthanides, and actinides. But none of them have replaced the rectangular form, because it is familiar, because it fits on classroom walls, because it is tradition. But maybe someday the shape will evolve, just like the science. Chapter 21. Periodicity beyond Earth. The periodic table was built on Earth. But what happens when we leave Earth? In space, conditions are different. Stars produce elements through nuclear fusion. Supernovae create heavier elements in explosive waves of energy. Black holes and neutron star collisions forge gold, uranium, and rare isotopes. Some elements may only exist for moments, deep inside stars. Others might form naturally on exoplanets with extreme conditions. The periodic table may be universal, or it may be a local phenomenon. Studying chemistry in space may reveal patterns we have never seen before, or it may confirm what we already know. Either way, it expands our understanding of matter and of ourselves. Chapter 22. AI and the New Alchemy. In ancient times, alchemists searched for a way to transform matter. Today, we have artificial intelligence. AI is now being used to explore the periodic table in new ways. It helps scientists predict new elements, model their properties, and simulate their behaviors. AI tools analyze massive data sets from chemistry labs. They find patterns that humans cannot see. They generate molecules with desired properties. They propose reactions before experiments are done. In this way, AI has become the new assistant to the modern chemist. Some call it the new alchemy, because it seeks to turn data into discovery, prediction into proof, code into compounds. And maybe someday, AI will help us find the next element before we even create it. Chapter 23. Periodic Trends and Hidden Patterns. The periodic table reveals trends: atomic radius, ionization energy, electronegativity, electron affinity, melting point, density, reactivity. These trends are not random. They arise from structure, from the arrangement of electrons, from the energy of shells, and the pull of the nucleus. AI can help us find deeper trends, hidden patterns, exceptions that become rules in disguise. It can even help identify new groupings, new families, or new periodicities in undiscovered zones. The table is not static. It evolves. It reflects not just what we know, but how we know it. Chapter 24. Why the periodic table matters. It is more than a chart, more than a teaching tool. It is a map of the universe, a key to understanding stars, soils, oceans, and organisms. It explains why some elements are essential to life and why others are toxic. It tells us how batteries work, how medicines are made, how the air we breathe is held together. It connects us to ancient stars that forged our atoms and to future technologies yet to be invented. The periodic table is not just for chemists. It is for everyone who wonders what the world is made of and how it all fits together. Chapter 25. A quiet ending. You have now reached the end of this boring journey. 6,000 words, one table, 2 centuries of work, from Aristotle to Mendeleev, from Lavoisier to Moseley, from laboratories to supercomputers. The periodic table has grown, and it continues to grow, slowly, quietly, predictably, like the lesson you just experienced. You now know the history, the structure, the trends, the future. You know the shape of knowledge and its periodic rhythm. Thank you for listening and for staying awake, or for letting your mind drift. That is fine too. This concludes your boring lesson on the hidden story of the periodic table. Good night, or good data.